All right, so in his book, from the 1200s, by the way, that's Leonardo Fibonacci, de Pascal or whatever, like that's not actually his actual name, right? But that's what he was known as. He theorized maximum number of pairs of rabbits resulting from newborn pairs of rabbits after 1 year. He assumed each pair produces a pair of rabbits after 2 months, and then another pair the following month. Basically, we have his sequence here, that after some time, they started realizing this was definitely not his sequence. This was a sequence that was already there. He just happened to see it, right? 1, 1, 2, 3, 5, 8. Hopefully, in this world of math, you've heard that sequence many, many, many times before. Especially for me, you had to write a poem last year about it, right? So we have this sequence, Fibonacci sequence. This is probably the most famous of the sequences, if they have fame. But what you find is patterns are very, very helpful, all right? Numeric patterns are helpful. Life patterns are helpful, okay? We can do a lot of inductive reasoning with patterns. And so this is one of the more famous ones, but this is an infinite sequence. And so if you look at that first definition there, we have the definition of an infinite sequence. It's a function whose domain is the natural number n. So we are doing counting numbers, okay? 1, 2, 3, 4, 5. Whose range contains the function values a sub 1, that just means my first value, up to a sub n, that just means my last value that I'm counting. This is an infinite series, so it keeps going. Which are the terms of the sequence? The nth term is called the general term. All right, so when you have a sequence, the general term means I'm going to write something so that if I said find term 12, you can figure out what it is based on this particular pattern. The domain of a finite sequence of n terms consists of the first n natural numbers. And so we talked about little Gauss. All right. His teacher said add up all the numbers from 1 to 100. Okay. The natural counting numbers is infinite. She gave them a specific set of numbers to add up. 1 to 100. 1 plus 2 plus 3 plus 4 plus 5. All right. And that's a sequence that is also pretty famous, a summation. That we can now do. So the nth term of 1 to 100 was 100. All right, that was the nth term there. And so that is what they mean by all of these little sub numbers. And then when we have general terms. So they've given us some sequences here. The general term for a sub n is 5n plus 3. And now they want us to give the first 4 terms of this particular sequence. Well, if I want the first 4 terms, I'm literally just going to plug in a 1, a 2, a 3, and a 4 and figure out the first 4 terms. So if I were going to do this first one, and we're not going to do all 3 just because we don't need to, we would say the first term, that would be a sub 1. A sub 1. Sometimes you'll see the first term, by the way, labeled a sub naught with a 0. Okay, so just pay attention to how they label those terms. But anyway, a sub 1 is going to be 5 times 1 plus 3. That is 8. A sub 2, that's 5 times 2 plus 3. A sub 3, 5 times 3 plus 3. And a sub 4, 5 times 4 plus 3. That is how you find terms in a sequence, right? Rather simple. Evaluate. Write an explicit formula for the value of a sub n and use it to find the 10th term, okay? So they've given us several examples here. You want to try to work it out to where you have just one base pretty much, where you don't have multiple n's, because that makes it more difficult. The first one, you really are looking for a pattern. That's all you're doing with sequences. I'm going to say, how do I get from the first term to the second term to the third term to the fourth term and so on and so forth? What are you doing? Yeah, I'm adding 3. Plus 3. So how does this work then? Each term you take and you add a 3. So if I start with the first term, to find the second term, I'm going to just say, well, that's going to be 17 plus 3. To find then the third term, I'm going to say, well, the third term is going to be the second term. That was 17 plus 3, and then plus 3, right? And we're going to keep doing this. The fourth term then is going to be 17 plus 3, right? That's my third term. And then plus 3, right? And so you'll notice that I'm adding 3, but I'm adding it a certain number of times. What am I adding? How many times am I adding 3 here? twice, but my n is 3. I'm adding it 3 times here. My n is 4. All right, so if I try to figure out how many times I'm adding it, I'm going to say, well, it's 17 plus not n, but what? N minus 1, right? And specifically 3 times n minus 1. That's how many times I'm doing that, right? So I'm taking a 3 and I'm multiplying, that's what repeated addition is, by n minus 1, right? I will say this is not usually the acceptable form here because that's not simplest, right? So if I wanted to simplify this, what would I do? This is basic algebra 1. What do I do? Distribute and simplify, right? So if I want a sub n, I'm going to distribute this guy, 17 plus 3n minus 3. Another way to write that would be 3n plus 14, right? So I am looking for a pattern. I'm going to write out my pattern, and then I'm going to simplify it into just a basic formula. You also notice this is a linear equation because this is a steady increase, all right? You will have exponential increases, and those will be exponential functions. You can have ones that are not necessarily a pattern that you see initially. Like over here, this pattern right here is not one that you may see initially. It's a square minus something, so it's a little bit more difficult. So they're not always beautiful like this, but we're going to get to that one in a second. It also has one more piece of it, 10th term. Once you have the explicit formula, explicit means I don't need anything in front or anything behind it. I can go straight to the 10th term by plugging in a 10. And so if I wanted to know what a sub 10 would be, I would literally just say 3 times 10 plus 14. 10th term. All right. Some patterns are a little easier. We're multiplying by negative 2 here. So that's going to be negative 2 to a power. Some are not as easy here. This guy right here, my first term, this is actually a sub 1. This is a sub 2. So sometimes you're not looking for a pattern between from term to term, because if you try to look for a pattern there, you're going to say, oh, plus 3, plus 5, plus 7, which is you're adding your odds. So it seems like that's what you're doing. There's another pattern that erupts here that's not as obvious. How do I get from 0 to something that has a 1? How do I get from 3 to something that has a 2? How do I get from 8 to something that has a 3? Okay, and so sometimes you're looking for this pattern, and it's not quite as obvious. The squares never are. Right? Writing the first 6 terms when the sequence is defined like this. So the first way that we did terms, they gave us the explicit formula. Here they actually give us recursive formula. Recursive formula is where you need the term in front of it to find the next guy. Okay? So explicit means, hey, here's what you're doing. I don't need anything else except the term I'm looking for. All right? Recursive says, okay, I really need the guy in front to give you the next guy. Okay, that's recursive. So it's just a pattern based on not right in the middle of it, but we need to start somewhere and then I can give you from there forward is recursive. So it says, right, the first 6 terms, they give me the first term, the second term, and then they give me the kth term, all right? They tell me how I'm going from term to term. I take the one in front of it, or the 2 in front of it. So if I have the kth term here, which is what it's saying, then I take the one right in front of him, plus 2 in front of him. All right? This is, by the way, how Fibonacci sequences. It just starts with 1, 1 instead of 2, 4. Okay? So, write the first 6 terms of the sequence defined. So if I want the first 6 terms, and they're saying I have to start with the third term, then I am going to say, well, the third term, or rather case of 1, is starting at 3, starts with 2 plus 4. All right? So that's going to give me a 6. Then the second term is going to add the 4 and the 6. That's going to give me a 10. The third term is going to add the 10 and the 6. That's going to be 16. The fourth term, and so on and so forth, is going to be the 16 and the 10. So sometimes they give you the formula not explicitly. They give it to you recursive, meaning you're going to have to walk to whatever term they want. Versus explicit, you can go straight to the term they're asking for. Okay? Make sense? All right, so let's look at finding recursive. I did grab this tip actually because I want to point out something that they tell you here, which is that any variable can be used to represent the sequence or subscripts. I, J, K, and N are frequently used for subscripts. If the general term is B of K, the previous term B of K minus 1, and the next term is B of K plus 1. So what they're saying is, just like in this example that we did, if they have a variable plus or minus, they're just telling you how far away from the one you're looking for you are. All right? So the one that we just looked at said K minus 1. That was the one right in front of K. And then it said K minus 2. That was 2 in front of the one you're looking at. So that's all they're doing here is direction. They're telling you what term am I talking about in relationship to the one you're looking for. All right? You will note that when we get into like summation, which is what we're about to do, they typically use like an I. Sometimes when I give it to you on your worksheets, I don't use an I because on my program, I represent something else. What do you think I represents on my program? Yeah, square root of -1. So my program will not use that. Mine will typically use a K instead of an I. And so in your book, very often you'll see a summation, which we're about to do using that I. Mine always uses a K because the I is going to confuse my program, if that makes sense. So it can be any subscript. It's like a variable. A recursive. So now we're going to tell the person how they get from one to another, not how they find a specific term. And so again, I'm going to look at this and say what happens to get from one term to the next. Well, again, I'm adding 3. That's clear. Plus 3, plus 3, plus 3. Okay? So instead of writing an explicit where I say find the 10th term, I'm going to tell someone how to find it using the term in front of it. All right? So if I were to start with the first term, I would say add 3. So if I want them to find the nth term, I am now going to use the subscript, the 1 in front of it. What would my subscript be here then? How would I say the 1 in front of it? If I'm looking for n minus 1, take the term in front of the one you're looking for, and how do you get to the next term based on what they gave me? I'm going to add 3. So I'm going to say the term in front of it plus 3. All right? Same sequence as before. They gave me the exact same ones, actually. -2. So if I'm telling it to multiply by the term in front of it, then I'm just going to say, well, if I'm solving for a sub n, I'm going to take the term in front of it, and I'm going to multiply by -2. All right? So all you're doing with recursive is you're just using the term in front of it. How do I get to it using the term in front or behind or 2 in front or whatever it is, whatever the case may be? All right? The product of n and every natural number less than n is notated by n with that little exclamation point. It is read as n factorial. Symbolically, n factorial equals n times n minus 1 times n minus 2 times n minus 3 and so on and so forth. FYI, 0 factorial is defined as 1. That is the most common mistake in like trivia questions. 0 factorial is 1. All right? 0 factorial is 1. That is how it is defined. It is not 0. All right. Let's look at this. All right. Use factorials to find terms of a sequence. Given a sub n equals 2 n factorial over n plus 1 squared. Find a sub 0, 1, 2, 3, and 4. Okay. Really quickly, factorial is automatically tied to whatever it is next to. Okay, so this does not mean multiply the 2 and the n and then take the product and do the factorial of the product. Okay, think of it as like an exponent. If I had 2x squared, I would only apply that exponent to the variable. I would not apply it to the 2. The same is true of the factorial symbol. Okay, it will make a difference in your answer. So you do the factorial first. Think of it almost as like a group. Factorial first for order of operations, then do the multiplication of the coefficient in front of that, okay? So if they wanted me to plug these in, and we don't have to do all of them for time's sake, but you would say 2 times 0 factorial over 0 plus 1 squared. 0 factorial is 1, 2 times 1 is 2, 1 squared is 1. That guy gives me a 2, all right? Does that make sense? And so you apply the factorial first. Let's skip to like 3 because 1 factorial is also just 1. So if I look at this next guy here, I would have, let's say, a sub 3. That's going to be 2 times 3 factorial over 3 plus 1 quantity squared. So 3 factorial. You have it in your calculator, by the way, probably under your probability menu. You have a factorial button. To do it manually, 3 is just 6, so you don't really need factorial button for 3, but 2 times, and you have 3 times 2 times 1, right? That's what 3 factorial means. 3 times 2 times 1, all the way down, obviously not times 0, or every factorial would be 0. And then 3 plus 1 is 4, 4 squared is 16. So this is what this guy looks like, okay? Yes, so we have what, 3/4? Oh. So this would be 3/4. All right, that's what factorial means. So I want you to practice. All right, first of all, let's talk about definitions of this. The end behavior of functions described using limits. If the values of a sequence approach a finite number, then the position number approaches infinity. The sequence is convergent. If the limit of is the limit of the sequence. If not, it is divergent. Okay, so if it goes towards a number, an actual number, it's going to be considered convergent. It converges. If it approaches infinity, then it's going to be diverges. You don't have an actual number you can say. This is moving us towards like a limit theory. So if I were to look at this, I'm trying to decide if this series is approaching a specific number or if it is approaching infinity. So we're going to use the same properties that we used in bell work here. So if I were to plug in a 1, a 2, a 3, a 4, and keep going, what would happen? Well, eventually, I'm going to be going on indefinitely. One of the ways to note that is infinity, right? And so I'm going to use my infinite limit shortcuts, just like I did in bell work. If I were having infinity approaching in the numerator and infinity approaching in the denominator, what would I be left with? A 5. And so this series, as n approaches infinity, the series is moving towards 5. All right? Which means it converges. Converges. That's what that term means. It's actually going towards a number, not a concept, right? Look at the next one. If this is moving towards infinity, what is this whole thing moving towards? Negative infinity. This whole thing is moving towards negative infinity. This guy would be diverges. Okay? Diverges. This last guy is a little bit of a trick question. This limit actually does not exist. So this is what's called an oscillating function, all right? Oscillating. Think of oscillating fans. What do? They spin back and forth, right? Oscillating sprinklers, same thing, right? They just go back and forth, back and forth. That's what an oscillating function does. Why does this bounce back and forth? Well, because I have a -1 to a power. When it's an odd power, it's going to be negative. When it's an even power, it's going to jump to positive. Then it's an odd power, it's going to jump to negative, right? And we're just ping-ponging back and forth, all right? We're technically not moving towards infinity, but we're also not moving towards a specific number because we're just ping-ponging back and forth. So this would not have an overall limit. It does not exist at all, but it still diverges. This is still considered diverges as a divergent function because it does not go towards a specific number. So whether it goes to an infinity, diverges, or whether it ping-pongs, does not have a limit at all. It's going to be considered divergent. So I'm going to say, what do y'all think my next number would be? Right, what would the next one be? What's happening to the bottom? The number on the bottom is getting larger, right? Use my limit theory. If my number on bottom gets infinitely larger, but my number on top stays the same, what is this guy eventually going to hit?
0.
Theoretically, it's going to hit 0. That is a number, is it not? So this converges or diverges? Converge. Summation just means take a sequence and add it up, okay? So we have sequences. Those are just numbers with commas in between. A series takes those commas and put pluses in between them. Summation is the notation for it. It's also, if you ever do a spreadsheet, that means add everything up in my column, right? So if you've ever used Excel or if you've ever used Google Sheets, that summation button will quickly add up the entire column. That's what summation means, add it up, okay? And so sequences are just the set of numbers. Series means I'm going to add up the numbers in my sequence. The sigma notation, sigma is the Greek letter that you see there that looks like an E. If you go to college and they have any type of sororities, that's what you'll see as well, but it's sigma. It just means that Greek letter, capital letter E. Looks like an E to us. It's a capital letter sigma. For the purpose of math, it means add up all the numbers. It has some boundaries here. So you will see a lower boundary. Here's where you will see your I. That just means your starting boundary. So this is the particular term in your sequence that you are starting with. And then your top guy tells you which term you're ending with. So you're going to add everything in between and the caps as well. It's going to include, you'll see it has an equal. So you're going to include your lower bound all the way up to including your upper bound. Think of it as closed brackets, okay? Example, if they want us to evaluate everything from I equals 3 up until 7 of I squared minus 2I, we would literally just plug that in. We would say, well, it would be a pain because it's just a lot of numbers. We would say 3 squared minus 2 times 3 plus 4 squared minus 2 times 4 plus 5 squared minus 2 times 5, that's not 0.5, plus 6 squared minus 2 times 6 plus, and finally 7 squared minus 2 times 7, right? That's all we're doing there. That's all we're doing. We're adding it up. And we're going to do some shortcuts with these where you don't have to actually do it all. I mean, there's some shortcuts you can do with these I's and these summations, but that's okay. We'll do it later on, not this particular section. Any questions on what summation means? Questions? It doesn't want a full summation. This is called a partial sum because they only want certain terms added up, all right? In order to add up the terms, you have to figure out how they go from one to the next, or it really doesn't help you, right? And so if you look, clearly we are adding 2, but it actually, if you look at how this works, this is my first term. You can set it up with your formula that you have. Or you can just say, if this is my a sub 1, I've taken that times 2, right? So I've taken 2 times that 1. This is 2 times the 2. This is 2 times the third term. And so you end up with 2 times n. All right? 2 times n. That is my sequence. So if I were to write the summation for this, I would say my formula here is 2 times n. Whatever term I'm on, I'm just multiplying that sub number by 2 to get that actual term. They want me to add up specific terms. So if I were going to write this out, I am starting with 5 and I'm going to 7. That's how I would write that. And then I would just plug it in. So I'm going to say 2 times 5 plus 2 times 6 plus 2 times 7. And I'm going to get that partial term, right? Questions on that? Partial term. Convergent. So same thing. All right, if you look right above it, it tells you the ones that we just did, example 8, that was a finite series because it actually gave me an end cap. Here, this is an infinite series. How do I know this is an infinite series? What tells me this keeps going? The ellipse, right? The ... at the end, okay? That says we're going to add 3 infinitely, all right? And basically, you're going to say, well, is this going to move towards a number or is this going to move away from a number? Let's look at the first guy, all right? Basically, if I were to take this right here, then I would say, well, I'm just adding 3 continually. So basically, I'm saying the summation from my first term to my infinite term is always going to be 3, right? I don't do anything to it. I'm just taking the first term. Well, that's 3. The second term. Oh, well, that's also 3. Oh, the third term. Well, that's also 3. And I'm doing it how many times? Infinitely. So just your logic skills should tell you this is moving towards what as my limit. If I add 3 continually, infinitely, what am I moving towards? Yeah. Yeah, it's moving towards infinity, so this is a divergent. This is definitely a divergent series, right? Okay, does everybody see why that's the case? Look at this next one, though. This little series here. I'm saying 0.3 plus 0.03 plus 0.003. So I start with 0.3. I add 0.03. I add 0.003. I add 0.0003. If I keep doing this, what's happening? That's just going to be this guy right here, right? Everybody agree? Like if I'm just adding a decimal place of a 3, I'm actually moving towards 3 repeating, 0.3 repeating. That is going towards an actual number, is it not? Yes? This is a divergent series. So, a convergent series. This is this guy right here. You can rewrite this. What's another way to write 0.3 repeating if I wanted it in rational form? It's a rational number. Right? Isn't 1/3 0.3 repeating? Right? Any repeating number can be written as a fraction. It's rational, right? Irrational numbers cannot be written as a fraction. Rational numbers can. 0.3 repeating. Remember, you just put your digit over however many digits you have repeating, right? And then reduce it. Remember the little shortcut for figuring out what a repeating number is? Okay. So this one is convergent. This is moving towards a specific number based on the pattern that they've given me. All right. So even though they're infinite, you can actually still have an answer. So the first one, I was adding numbers infinitely, and I'm like, no, that's diverging. That's moving towards infinity. The second one, I'm still adding numbers infinitely, but I can see that adding those numbers infinitely is actually bringing me towards a number. And so you can use those to, even on infinite series, to tell me if it's moving towards or away from a number. Okay? Questions on infinite series?